Um, Good afternoon, everyone. So I'm going to be sharing some information about challenges we have for low-rate applications. So first of all, why low-rate applications? This on the label for everyone. So every year we go through this, choosing the right product for our needs. What is the correct label rate? What is the how can you maximize the efficiency of the product that you're applying? Keeping yourself safe, saving money, helping the environment. All of these things actually play a very big role in actually choosing the right product for you. One of the important things for the districts is actually lower operational costs. And what do I mean by that? So when you have a low rate application, you have a reduced ferry time. So if you have a regular aerial application, like in using an aircraft, so number of times that the aircraft has to go back and forth to refill actually is lower. Thereby you're saving on fuel costs and also on wear and tear on the equipment. And if you're actually contracting, then the time that the aircraft is up there in spending for you for doing all the applications. But as Scott Stock was there before, and quite a bit of interest that we got from the questions that came after his talk, the topic of the right time now is the drone. So how do you use drones to actually do applications? So we have several spreaders that are out there in the market now for using drones, but drones have a limited capacity for us right now with respect to timing. So how long can a battery last for a drone to do the applications? So those kind of scenarios when the low rate applications actually make a lot of sense. So you can have efficient battery usage and also a longer application time with the drones that you have, if you have a low rate application product. Okay, so characterizations, we do this. This is the traditional way how we set up characterization. So you put some buckets or totes, containers you see on the picture here, and then you let the aircraft fly on top of it, and then you collect the materials back and put them in the cups, and you evaluate the weight of those granules, and then that's how you do characterizations. Now, some of the important variables that go with these characterizations. Coefficient of variation. I'm sure many of you would have heard about coefficient of variation, but that is actually an important variable when you're actually doing these larval granular characterizations. What does it measure? It actually measures the extent of variability in your application. Well, there's a lot of statistical jargon to it, but it's on Wikipedia. So if you search coefficient of variation, you'll get that. But in a nutshell, what it is that you might get a mean or an average for whatever you're doing. But that average, what does it actually represent the whole population, or does it represent only a small portion of the population? So let's take one scenario here. So here in this graph, you can see from A to H, these applications had different trends. So the bar graph actually keeps increasing. And in the end, you see peaks on there. So a coefficient of variation here, this is not actually, if you get an average of this particular sampling, you won't be able to get the right average. The average is not actually representing what's happening in the field. So in this kind of a scenario, you will have a COV, which is actually high. So anything at the range of 1 is pretty high coefficient of variation, just saying that the data is too variable. The mean that you have is not really the mean that you can actually use for deciphering anything, because it's actually have these infrequent distributions. But let's consider another scenario. In this scenario, you have even distribution. If you look at the COV for this one, it is pretty small. It's only 0.03. And this is actually, if you get a mean from this distribution, then your mean or average is actually more reliable. So whatever you're trying to achieve is more reliable. So in our recommendation, we always stick with the COV of 0.3. Less than 0.3 is better when we're doing these characterizations. And another important point with these applications is the minimum preferred application rate. How much should we apply? At any one point in the swab, how much is the minimum that you need to have. That varies by habitat and species and the product that you choose. But each product will have a minimum application rate below which you do not want to apply at any one point of the swath. Okay, so what is an uneven distribution? We see this very much in lower applications issues. I mean, we do see this when the equipment is not calibrated and configured properly, that these uneven distributions, even in a high rate. But typically, it does occur more often in the low rate applications, hence this focus, and we're trying to look at it. So in this graph, you have pounds per acre. And these are data from the tubs that have been placed across the swath here on the x-axis. And these are actually the pounds per acre applied. And you see this line, the red line, that's the minimum preferred application rate. That is 2 pounds per acre for this particular product. And your targeted application rate, which is the green dashed line, that's where you want it to be. That's your ideal. That's what you're actually targeting. Look at the average here. That's 2.6 pounds per acre. Can you trust that average? Look at this peak here. At one point of time in the swath, you're getting 10 pounds per acre. Some about 9.8 pounds per acre. So there's quite a bit. So if you actually get this kind of a distribution, then you have an uneven distribution. Not only that, that's over applications. You're wasting product because all of that is going to be staying in one area of the swath. Although your targeted swath is 55 feet, and that's what you are going to be using, but your actual swath is only 15 feet. And that's because this is actually streaking, and you have a problem with the equipment, and it is actually applying in one area, and it is not distributing evenly. Okay, let's see some low rate application examples. How can we actually resolve them? So I picked vector prime because it's easier. I'm more familiar with the vector prime, but this applies to any other low rate application product. You can choose anything that's out there. And for this, actually, according to the label, for post-flood situations, if it is not polluted, it's about 1.25 to 4 pounds per acre. That's a really low rate. There's almost half of some of the traditional larvicides that are out there. So achieving this, what are some of the challenges that we might actually come across, and how best to resolve them? Up front, collection containers. When you're doing these characterizations, before even you go into equipment problems, first things that we have seen in the field is actually what kind of collection containers do you use? So this is a typical, as you see in the left picture, where you actually line up all the containers, and you have an aircraft that is actually flying on top of it, and you collect the deposits, and then you look at how many pounds per acre at each one point of the swath the application was. Now, in this case, what we did was we did a comparison between tote boxes, which have typically a little bit of a bigger opening, and then a bucket, which is actually a smaller opening. So is there any difference? Traditionally, a lot of people use buckets. We've used buckets a lot. But what is the difference? How do the tote boxes actually perform? And all other things here are similar. So same aircraft, same opening, same product, wind speed, temperature, everything is same because you see both of them are lined up exactly. Is there a difference when you do these kind of applications, especially when you have a low rate product that you're trying to evaluate, characterize your equipment for? Let's look at the results. So left graph is for tote boxes, and the right graph is for buckets. Again, everything is same. The only difference is whether they were actually buckets or totes. But other than that, all other factors are similar. And you see on the left one how the distribution is a little bit more even for the product. But if you look at the bucket on the right side, there seems to be some peak. Again, it's same equipment. Everything is same. How can this be? It looks like actually the amount of opening, the mouth of the collection container that you keep actually has a lot of impact on these low rate applications. This is more profound in low rate applications than in high rate applications. So this is something that we have to keep in mind when you are characterizing some of the equipment, is to make sure that you have a container that actually represents a little bit of a bigger opening than a typical bucket that's a smaller and circular. And if you look at even the COB here, that is actually 0.3, it's pretty good. That's what you would recommend for an equipment for a low rate application. So this one says this is qualified, but on the right side with the bucket, this says it's 0.7. That means no, that run was not qualified. That equipment is not actually doing what it's supposed to do. So that there itself, you have a confusing information. So you got to choose the right method to put it there to collect your granules in order to do the characterizations to see if you're able to configure your equipment properly. Okay, moving on to the next one. So this is actually a predicted swath pattern. So once you actually have a typical pattern, you put it in a software or some Excel sheets where you actually do these simulations to see how well, if you do an aircraft back and forth pattern, how will your deposits be. Again, on the left side you have tote, on the right side you have the bucket, everything else is the same. And you can see the streaking that you're actually getting in the bucket. That's misinformation, just because you had the wrong type that you put under the aircraft to actually collect your containers. But on the left side with the tote, it says everything is good. And when you extrapolate this for 360 feet of back and forth, you're doing perfectly fine, no problems. So good one to keep in mind when you're actually characterizing these equipment. Okay, I'm going to go through a couple of case scenarios pretty quickly here. This one is actually a fixed wing aircraft. There was an issue where there was streaking. So what is the best way to resolve it? Actually, installing a custom roller actually helps a lot. So that actually improves the swath. The rollers are available for different kinds of equipment. Even Isolar actually has a roller now. So you can use those to actually equally get the product out. And this helps especially in low rate applications. There are rollers that can actually handle smaller application rates very efficiently than higher application rates. So roller is a good solution if you want to go with the roller method for applications. So for this one, it was 4 pounds per acre target and then optimal swath with this 90 feet. So we'll go through a couple of graphs here. You're familiar with the graphs like just before. Good even distribution, and then COV was only 0.25, which is good. The equipment is doing good and the calibration is pretty good. On the right side, the predicted swath also indicates the same data. So that one is good. Let's go into case 2. This one actually is a rotary wing aircraft. Again, it shows uneven application. What is the best method to resolve this? And in this time, in this equipment, in the picture, you see there's a tube that is coming out. There's actually a boom that's actually attached to that tube. And the boom actually has 4 points where it actually discharges the granule. And this is another way of actually evenly distributing your low rate granule. And you have smaller hopper openings, testing those different types of hopper openings, and then the boom that was there actually helped in alleviating the problem, so you have more even distribution across the path. For this one, was 5 pounds per acre, and the optimal swath was 75 feet. There's a couple of graphs here, and if you see on the left, again, even distribution, no issues. COV was 0.3, which is good, and that's what you want it to be. On the right side, if you see the simulation, the graphs look really good for application. All right, so moving on. Some of the key considerations. So what would you do? First and foremost, for characterizing the equipment, you want to use the right type of container that you're going to place under those aircrafts or drones for that matter. So totes are a little better, mainly because of the opening that is there. So bigger the opening, better you're going to be in estimating closer to your true value of the true average of what you're actually getting. Low rate applications are going to be the future, especially with drones, and we have limitations on all of how much it can carry efficiently, and also increasing the payload so that you're able to cover more area. So moving towards that, we need to pay attention to all of these important features so low rate applications can be effectively applied. Existing equipment can be modified and configured accordingly. It's not a big deal. You just have to be focused on the characterization to identify the problem first. And when you identify the problem first, then you'll be able to resolve them pretty quickly, regardless of whatever equipment you have.